In this video, we're going to be going over two learning objectives all about Newton's law of universal gravitation and how to apply it. The first learning objective we're going to be covering states that I can model a system of two objects interacting at a distance using force vectors. The second learning objective that we're going to be covering states that I can apply Newton's law of universal gravitation to determine the force of attraction between two objects. Let's break down some of the vocabulary. First one is pretty simple. We have just force vectors, which we've dealt with before. So just think about how do you draw vectors, free body diagrams. But the difference is we're going to be applying this for forces that are interacting at a distance. So it's not forces that are right next to each other, not objects that are right next to each other. How do you handle things that act at vast different distances? The verbs for this is that you can model a system, which for many purposes in physics is that you can draw it or represent something abstract using a drawing. For the second learning objective, we are going to be applying Newton's law of universal gravitation. So that is a new term here that we're going to be learning to determine the force of attraction between two objects. So the verb for that one is that we're going to be applying an equation and we're going to be determining the force of attraction between two objects. So essentially, we're going to be rearranging an equation, solving, plugging in values. Let's now go over Newton's law of universal gravitation. This is probably one of the most famous laws that Newton came up with. Of course, we've studied him before with the Newton's law of motion, the first, the second, and the third law of motion. This is the one that commonly gets attributed with him sitting beneath an apple tree and having an apple fall on his head. This is the equation, right to the left. We have the force of gravity is equal to some big G, which is called the universal gravitation constant, and it has a really interesting value with some interesting units. The value for big G is 6.67 times 10 to the negative 11th. That's a really small number, because remember, negative exponents means an incredibly small number. And the units to this are newtons times meters squared divided by kilograms squared. Those are some funky units, and we'll quickly go over why that's the case in a moment. But let's look at the rest of the equation first. After this universal gravitation constant, we have m1 and m2. Now, sometimes this is represented as a large m and a lowercase m. Well, the idea is that it's two different masses, because each of these m's usually in physics represent mass. So we have m1 being the mass of one object and m2 being the mass of the second object. Turns out that gravity, or the force of gravity, depends on not only the mass of one object, but the mass of the other object as well. This explains why the same person standing on the Earth and standing on the moon would weigh different amounts, because weight is actually just the force of gravity acting on a person. So we have one mass times the other mass, and then we're dividing all of that by r squared. Now, r is the distance between the two objects, measured from their center of mass. So you measure distance between two objects from their center of mass, and that is the r value here. Now, there are some limitations to this equation. This equation is assuming that you're not inside of another object. So if you were inside the Earth, so if you dug miles into the Earth, you would weigh a different amount because you're closer to the Earth's core, but also because some of the mass of the Earth is above you now, which would be pulling up. So you would have some of the mass of the Earth pulling down and some pulling up, which is going to cause the equation here to be different. I wanted to quickly go over the case where you're actually inside the Earth, because it's rather fascinating. This graph right here represents what the Earth would look like, or the gravitational attraction of the Earth would look like when you go inside the Earth. And notice it peaks between the inner and outer mantle. It's because of the different densities of substances. Let's take a closer look at this equation again, but more importantly, let's take a look at the units of the gravitational constant, the universal gravitation constant. So the units are newtons, which is typically a unit of force, times meters squared divided by kilograms squared. Now let's go back to the equation here. Let me write this out. If we had a newton times a meter squared divided by a kilogram squared, that's the unit of G, by the way. And we multiply that by a kilogram, because that's the unit of the mass here, times a kilogram. Oops, and I forgot the kilogram squared back, because there's this kilogram squared. And then we divide, because this kilogram is from mass 2. And then we divide all of that by r squared, which the units of r would be meters squared. So that's coming from over here. So I just labeled where all the units are coming from. Watch what happens. Kilograms squared on the bottom are going to cancel both the factors of kilogram on the top. And the meter squared on the bottom here is going to cancel the meter squared there. And what we get left with is newtons. So we get left with newtons, which is exactly what we should get because a force is in newtons. Another way to have done this is we could have solved this equation for the universal gravitation constant, which would then be force times the distance squared divided by mass times a mass 1 and mass 2, which would ultimately get us a Newton times meters squared divided by kilograms squared. So that's another way to prove that the units of this universal gravitational constant would be newtons times meters squared divided by kilograms squared. So that's the equation for Newton's law of universal gravitation. Turns out this equation right here, besides some of the cases where I mentioned before, is always true. Now previously, we said that the force of gravity is equal to m little g, where little g was our 9.8 meters per second squared that we're so familiar with. It turns out this is a special case of Newton's law of universal gravitation. Newton's law of universal gravitation would also agree with this statement so long as two things are true. First, the radius of the Earth is being plugged in for r here. So what's being plugged in for r is the radius of the Earth. Second thing that must be true, the mass of m1, or one of these masses, it doesn't matter which one, honestly, is equal to the mass of the Earth. This equation right here, this Newton's law of universal gravitation, simplifies down to the simpler mass times little g constant when we're talking about on Earth and we're talking about an object being on the surface of Earth, specifically at sea level. If the object was not at sea level, like let's say, for example, the object was on top of Mount Everest, the radius would increase. The distance between the person and the center of the Earth would increase, which would decrease the overall force of gravity. So in other words, if you're standing at the top of Mount Everest, you weigh less. Well, let's talk about this first learning objective, about modeling two objects interacting at a distance using force vectors. And that's what I have drawn right here. So we're going to take the two objects, being the Earth and the Moon. So the Earth and the Moon experience a gravitational pull from one another. Now, most people think of the Moon being pulled on by the Earth. But it turns out, because of Newton's third law, which, let's go back and remember what Newton's third law states. Newton's third law states that whenever one object applies a force on another, the second object also applies a force on the first object. So this force that I've drawn right here to the right is the force that the Moon is pulling on the Earth. It turns out that that is equal to the force that the Earth is pulling on the Moon. So the force that the Moon feels because the Earth exists is the same magnitude, but opposite direction, that the Earth feels because the Moon exists. And they're both this equation right here. In this case of the Earth and the Moon, m1 might be the mass of the Earth, and m2 might be the mass of the Moon. This r here would be the distance between the Moon and the Earth, and of course g never changes because it's a constant. This diagram here, right here, is what that first learning objective is talking about. It's essentially just applying Newton's third law for forces that act at a distance. The first one we're learning about is gravity, but there are other forces that act at a distance. For example, the electrostatic force. So the force that maybe a proton feels towards an electron. That attraction, because of their difference in charges, is another example of a force acting at a distance. The magnetic force as well. The fact that two north poles repel each other, but a north and a south pole attract each other, that's another example of a force acting at a distance. We're going to take a look at an example. In this example, we have the Sun and Jupiter. Now, Jupiter is really massive. Now, of course, it doesn't come close to the mass of the sun, but it is the second largest in terms of mass object in our solar system. And we just said that both objects feel a force of gravity. In the previous example, it was the Earth and the Moon. In this example, it's the Sun and Jupiter. They actually feel the exact same force. Now, the Sun doesn't move a lot because it's more massive, so you would need a larger force to get the same kind of movement from it. But it turns out the Sun does move. The Sun, now this is exaggerated in this picture, the Sun does wobble. It has this little tiny orbit that it goes through. Now, it's not orbiting an object, it's orbiting the center of mass between these two objects, between the Jupiter and the Sun. So it wobbles, and this actually confounded early astronomers because they got telescopes that were precise enough to notice that the Sun and other celestial objects that had orbiting bodies around it, so stuff orbiting it, would oscillate a little bit. So they would wobble a bit. They might look at it like it's doing this kind of motion, like it's going around and it's doing a little jiggle, essentially. And that's because the Sun does feel a gravitational pull towards Jupiter as well. This also explains the tides. The tides are explained through the force of gravity that the moon exerts on the water. So the water feels a force of gravity by the moon. So that's why you get a high tide when the moon is right overhead, essentially. And you get a low tide on the places that it's not. Turns out the Sun also does that. So if you had, let's say, the Sun on the left side and the moon on the right side, this would pull the water to the left and to the right, which would really suck in the water on the top and bottom here. So there's different configurations that give you different amounts of tides. That's why tides are not so simple. It's not that every 8 a.m. the tide is 1 foot higher than base level. That's why you have to look at a tide chart in order to see what are the tides for a given day and a given time. And they change throughout the year. Cyclical, but you still have to look it up because it's a bit more complicated than a simple cycle. Now let's go on to the second learning objective, which is all about applying this equation. It's about using the equation to, of course, determine the force of attraction between two objects. Or we could use it to determine any other of these variables if we, for example, we knew what the force of gravity was. Here's an application of that. So the question is asking, what is the force of gravity between two apples? They're both 0.1 kilograms, so they're both 1/10 of a kilogram or 100 grams, and they're 1 meter apart. Typically, we don't really think of two everyday objects as having a gravitational attraction between them, but it's true that that is the case. Every object that has mass exhibits a gravitational field. Every single object that has mass is pulling on every other object that has mass. So these two apples are actually pulling on each other. And the force of gravity is always towards the other object. Now we'll see why we don't often think about the gravitational attraction between two everyday objects. So the first step is we're going to write out Newton's law of universal gravitation. So that is the force of gravity is equal to gravitational constant times one mass times another mass divided by the distance between them squared. For this equation, the masses are really easy and the distance apart is probably the simplest distance apart you could possibly choose. So what we got to do is we have to write out the value for the gravitational constant mass and then multiply that by another mass. Then we're going to take the distance and square it. Solving all that, we get that the answer would be 6.67 times 10 to the negative 13th times 10 to the negative 13th. That is an incredibly small number. This is an incredibly small force. You would have a really hard time ever measuring this force. Yet, to prove Newton's law of universal gravitation and to get this value right here, scientists actually did have to measure forces. Maybe not quite this small, but to the negative 10th, to the negative 11th, to the negative 9th. Possible, yeah. Let's go over quickly, how is it that scientists actually measured such a small constant, like the constant for the universal gravitational constant? This was a rather fascinating experiment, especially considering that this experiment was done before there were cars. This experiment is extremely old. this experiment was long before modern technology, and yet they were able to measure the force of gravity between two regular objects, something we normally don't even think about. How they did this was they took this rod with two balls and suspended it on a wire. And then on that wire, they put a mirror. Now, this wire can twist, and they knew exactly how much force was required to twist it a certain amount of degrees. And then what they placed next to this rod were these two giant and incredibly heavy spheres. Those spheres were made out of some kind of lead or other heavy metal. So they're incredibly dense. They have a lot of mass, which we know would help with the force of gravity. The heavier the object, the higher the force of gravity. And they placed this rod near the other spheres, near so that, again, the force of gravity increases. And what they did was they noticed that this rod would twist slightly. So this rod would twist slightly because of the presence of these giant spheres. And then they would shine a light laser, so they would shine a laser onto the mirror. And because the wire has twisted, the mirror would shine the laser at an angle. And what they did was essentially measured that angle and found from that the force of the attraction between these two metal spheres. Let's do one of these problems together. So for this problem, you have a question asking, how far away from Earth's surface do you need to be such that the force of gravity you feel from the Earth is cut in half? One key thing to realize is that we're looking for R. We're actually solving not for the force of gravity, but we're looking for R. What we're going to do is we're first going to rearrange this equation and solve for R. So we can swap the places of R squared and the force of gravity. So we get R squared is equal to big G m1 m2 over the force of gravity. And then we can square root both sides. So this gets us that the distance is going to equal the square root of G m1 m2 over fg. This is a type of physics equation that's very common. The idea that we're going to change one variable by, cutting it in half or doubling it, and we're going to see what the effect on another variable is. Before we go on any further, let's first label this R1. It is the original radius. Let's say it's the radius at sea level, so the radius on the Earth's surface. Now, we're going to write R2. R2 this time is going to have the force of gravity get cut in half. So how are we going to represent that mathematically? How are we going to represent the force of gravity being cut in half mathematically? Well, we're going to write G, mass 1, mass 2, and we're going to divide by 1/2 times the force of gravity. So this represents half of the original force of gravity. So now we have a fraction in the denominator. We can flip that and multiply. So what we have is the square root of G m1 m2 times 2, that's still under the radical, divided by the force of gravity. And now what I'm going to do is I'm going to rearrange this a little bit. If you should remember from your algebra classes, we have things being multiplied inside the radical. Well, multiplication follows the commutative property. I can switch the order any way I want. Also, I can take that 2 inside of the radical and bring it out of the radical, but in its own radical. Let me show you what I mean by that. We can take square root 2 times the square root of this G m1 m2 all over the force of gravity. So that's what R2 equals. R2 equals the square root of 2 times the square root of G times m1 times m2 divided by force gravity. Now, what we should notice is that the expression to the right, besides the square root 2, looks almost the exact same, and I probably should show the arrow going the other way, because what we're going to do is a substitution here in a moment, looks exactly like R1. What we're going to do is we're going to replace the expression that I circled with R1. So this is saying that R2 equals the square root of 2 times R1. So the new radius is equal to the square root of 2 times the old radius. This is a really clever trick for when you get a problem that's about doubling or halving or quadrupling one variable. So it doesn't give you the actual value to that variable. It just says, okay, let's just say we double it. Notice I never gave in the problem how big the force actually was. We didn't need to know that. We just needed to know how much did it increase. Turns out it got cut in half. And from that, we could figure how, compared to the original radius, how does the new radius look? And what we know is that the new radius would be square root 2 times the old radius. Now, if we want an actual value, what we could do is we can plug in the radius that was given, and that would give us an actual value for the new radius. As usual, I leave you with 2 practice problems. For the first practice problems, we have 2 masses, m1 and m2, and they're separated by a distance r. So let's give some values for that. M1 is 5 kilograms, M2 is 10 kilograms, and R is 2 meters. So you're going to calculate the gravitational force between them. This is essentially just take those numbers and plug them into the equation that we've seen before, the Newton's law of universal gravitation equation, and solve for the force. Now, what I would also want you to do is to draw this. Don't forget to draw it, because that's practicing that first learning objective, all about representing forces acting at a distance. The second one, what you're going to do is, now we're going to be given the gravitational force. So we're going to be given a gravitational force of 3.34 times 10 to the negative 9th newtons. And one object has a mass of 2 kilograms, and the distance between them is 1 meter. So what did I not give you? Well, I didn't give you the mass of the other object, so that's what you're going to solve for. So you're going to take this equation and solve for the second mass. We've always have g. I've given you the mass of 1, the distance away, and the force that they experience. So you're going to rearrange the equation and solve for mass 2.